Morning, everyone. So, network theory for HAL exam. So, the syllabus, if you see the syllabus as given in the what you call the notification, it's similar to that of GATE. Okay, you can expect similar to that of GATE. The syllabus is similar to that of GATE, but there will be 100 MCQs from what you call your technical. So, you'll get only MCQs in this HAL. So most of those will be direct questions. Okay, concept-oriented direct questions. You don't have to solve much on those. But so the syllabus you can broadly share like this. The syllabus is like basic concepts and laws, nodal and mesh analysis. And again, the subject is same for EC, EEE, both for electronics as well as electrical. So basic concepts and laws, nodal and mesh analysis, circuit theorems, inductor and capacitor, first order RL and RC circuits, second order circuits, sinusoidal steady state analysis, three-phase circuits, magnetically coupled circuits, frequency response, passive filters, and two-port networks. This is the syllabus. In this, actually, this three-phase circuits is only for triple E guys, not for electrical guys, not for what you call EC electronics.
Sir, INE people also allowed, so that
Okay.
that may be for INE as well. INE are allowed under EC stream, sir.
Okay, INE are allowed under EC stream for HAL. Okay.
Yes.
Actually, HAL is basically an production, what you call major thing, aeronautical and production. So for electrical and electronics, they'll be they'll allow multiple streams so that you can join it. I think, yeah, this is only for triple E. Three-phase circuits is only for triple E. It won't be there for IN and ECE.
Yeah.
Okay,
Yes.
and yeah, so sinusoidal steady state analysis. So everything is common, rest everything is common. There are some portions which only triple E guys has. We'll discuss them as we go on. Okay. Next, basic concepts. So electrical circuits, as the subject name network theory, some people call it as circuit analysis, some people call it as network analysis. So what actually it is so electrical network and electrical circuit, they use the word circuit and network interchangeably sometimes. So an electrical network is an interconnection of electrical components or a model of such an interconnection consisting of electrical elements. Okay, an electrical circuit is a network consisting of a closed loop giving a written path for the current. Okay, understood the difference. So some universities call it as network analysis. Some universities call it as circuit analysis. So the name is used interchangeably. If you go into details, the difference is network is any interconnection. Any interconnection of electrical components is called as electrical network. But a circuit will be any interconnection with a closed loop is called as a circuit. Okay, so you can see this here. This is having R1, R2, R3, three resistors connected, and there is no closed loop. So this you can call it as an electrical network, and there is a closed loop here. So this is an example of electric circuit. Okay, so by the definition, you can say all circuits are networks, but not all networks are circuits. Okay, every circuit is a network. Okay, in the sense, network can be any interconnection. It may have closed loops, may not have a closed loop. So when there is a written path to the current, then you can call it as circuit. So there are fundamental quantities. I don't know why it is not getting full screen. Okay, fundamental quantities. We are having two fundamental quantities: charge and energy. The electrical quantity is a property of what is charge? The electrical quantity is a property of atomic particles of which all matter exists. Law of conservation of charge states that charge cannot be created or destroyed, only transferred.
Sir, please keep underlining when you speak.
Yeah,
Sir.
yeah. Yes, yes. Actually, I'm thinking of full screen.
Yeah, yeah, sure.
Yeah. So charge is electrical property of which all atomic particles are made. So law of conservation of charge states that charge cannot be created or destroyed, only transferred. Okay. So electric current is defined as the time rate of change of charge passing through any cross section of a conductor. So what is current? Current is the time rate of change of charge. So I is defined as, sorry, as I think the IGC tool is better than this. dq by dt. Okay, time rate of change of charge is defined as current. Okay, and what is the units? You can solve. What are the units of charge? Charge is measured in coulombs. So this is coulombs per second or amperes. Coulombs per second or amperes. Energy is the capability to do work. So electrical potential or voltage is defined as work done in moving a unit positive charge from a reference point to a specific point inside the field without producing an acceleration. Okay, it's the work done in moving a unit positive charge from one reference point to another is known as voltage or potential difference between those 2 points. Okay, the work done in moving a unit positive charge from one point to another point, another reference point. That is nothing but voltage or potential difference between those 2 points, and the unit is volts. Okay, so potential difference or voltage. Voltage is nothing but dw by dq. Work done in moving a unit positive charge from one reference point to another reference point is nothing but your voltage or potential difference. Okay, so this is measured in volts. Okay, next coming electrical power. Electrical power is nothing but rate of performing work per unit time. The unit is watt. Electrical power is defined as rate of change of work, or dw by dt. Okay, so from this you can write it as dw by dq into dq by dt. As we know, dq by dt. So from this, what you can write, dw by dq is nothing but your voltage, and dq by dt is nothing but your current. Current is nothing but power. Okay, so power is measured in watts. Okay, power is measured in watts. What is power? Power is the work done in moving a unit. Sorry, work done. Voltage is nothing but work done in moving an unit charge from one reference point to another reference point is nothing but voltage or potential difference. And what is current? Current is time rate of change of charge is nothing but current. And what is power? Power is work done, rate of work done. Okay. Next coming is nothing but Ohm's law or resistance. Ohm's law and resistance. Okay. What does an Ohm's law state? What does Ohm's law state? Ohm's law states that the voltage across any conducting material is directly proportional to the current flowing through the material under constant physical conditions. This is important, under constant physical conditions. What are the constant physical conditions? Temperature and pressure. Okay, what does Ohm's law state? Ohm's law states that the voltage across any conducting material is directly proportional to the current flowing through the material under constant physical conditions. Okay, V is proportional to I. And what is the constant of proportionality? R into I. Okay, so R is, again, it is a property of the material. R is the property of the conducting material by which it opposes the flow of current. Unit is ohm, denoted by omega. R is equal to, R is resistance, and what is it? It is denoted by omega, and the units are ohm. Okay, so important in Ohm's law is under constant physical conditions. Voltage is proportional to current under constant physical conditions such as temperature and pressure. So Ohm's law and resistance states that the voltage across conducting material is directly proportional to uh, current flowing. So there is something called as Ohm's law triangle. So this is V. If I want V is nothing but I into R. Okay, V is, if I want V, it is nothing but I into R. I is nothing but V by R. R is nothing but V by I. Okay, so every physical property. Uh, so resistance, as I said, it's a physical property. So okay, similarly, we will have a power triangle. If you want power, it is nothing but V into I or I into V. If I want I, it is P by V. If I want V, it is P by I. Okay, this is power triangle, and this is your Ohm's law triangle. Okay, and there is properties of resistor. Resistor is a physical quantity, so it depends upon the physical values such as cross-sectional area and length of the conductor. So R is equal to rho L by A. R is nothing but rho L by A. What is rho? Rho is resistivity or specific resistance. Resistivity or specific resistance. So anyone define what is specific resistance? Okay, R is equal to rho L by A. Rho is specific resistance, L is the length of the conductor, A is the cross-sectional area. Okay, so resistance depends upon length and area. So it is inversely proportional to the area. So the larger the area, the resistance will be low. The lengthier the what you call cable or what you call material, the resistance will be high. So whenever you see practically also the for some what you call applications where you need to lay cable for a long distance, so what they do is they'll take a more cross-sectional area, or if I need a 10 square mm material, I'll use a 16 or 20 square mm, so that what happens, my resistance, there won't be a drop of resistance there. Okay, this is how they do it. What is rho? Rho is resistivity or specific resistance. So if you want to define resistivity is nothing but resistance of a unit cube. Okay, so rho is equal to R into A by L, right? So if I take one or unit cross section area and unit length, what happens? This is rho is equal to R, right? So rho is nothing but it is defined as resistance of a unit cube. Okay, or resistance of a of a material which is having unit cross section area and unit length. Okay, whether it be meters or centimeters or kilometers or anything. So resistivity is defined as resistance of a unit cube. Okay, so you can directly write this as resistivity units are ohm meters. What are the resistivity units? Nothing but ohm into area is meter square by meter. So you will get meters. Ohm meter is the unit of resistivity. Okay, again, what is conductance? Conductance is the reciprocal of resistance. Units are Siemens or mho. Okay, conductance is the reciprocal of resistance. Units are same as, so G is equal to 1 by R. Okay, so conductivity is nothing but specific conductance, or conductivity is nothing but reciprocal of resistivity or specific resistance. Okay, sigma, it is defined equal, it is represented by sigma. Okay, so this is, the units are mho. And what are the units of this? Mho per meter. Okay, so conductance, conductivity, resistance, resistivity. Okay, so next is the concept of open circuit and short circuit. Okay, if as we have seen resistance, we just talk about resistance and all. So if resistance is 0, what happens to voltage? Voltage is 0 again. V is equal to I into R. The voltage is 0. This is short circuit. Okay, as a property of a short circuit, is resistance voltage is 0. Okay, there is no voltage or there is no potential difference. Okay, or theoretically, if I see when the resistance is 0, voltage is 0, denotes a short circuit. So short circuit in the sense I into R is 0. So R is 0. So that means I is infinity. Okay, generally V is equal to IR. So R is V by I. Sorry, I is V by R. If R is 0, what happens to current? Current is infinity. So theoretically, a short circuit can take, theoretically, it can take any amount of current with 0 voltage across it. Okay, what is a short circuit? Short circuit can theoretically take any amount of current, with 0 voltage across it. So 0 voltage is a property of a short circuit. Generally, if you ask short circuit, so people will say it's 0 voltage or 0 resistance. Okay, that means it can take any amount of current. So similarly, what is an open circuit? Open circuit is nothing but R is infinity. Okay, so what is current? Current is 0 here. Okay, so current is 0, V by R. So this is 0. Resistance is 0. That means current is 0. So open circuit can theoretically have any amount of voltage. Similarly, any amount of voltage with 0 current across it. Okay. Open circuit can theoretically. So I is equal to VR. Sorry. V is equal to I into R. So R is infinity. That means it can take any amount of voltage across it with 0 current through it. Okay, similar. Generally, open circuit will have the full voltage. Okay, full voltage which can appear at those points, at the open circuit points. Okay. So active and passive elements. So active elements or passive elements. So active elements. So there is what you call classification of elements into active and passive elements. What are active elements? Active elements in the sense energy sources of energy, nothing but active elements. And passive elements are energy consumers, sources of elements and energy consumers. Okay, sources and consumers are passive elements. Okay, sources, what all sources we have? Voltage source and current source. Again, there are independent sources and there are dependent sources. Okay, so you have voltage source and current source and independent sources. And dependent sources, we have 4 types: VCVS, VCCS. Okay, so let us see one by one. So inherently, all sources are non-linear in nature. Okay, non-linear. All the sources are non-linear in nature. So we'll see what about the passive elements. We'll see those. They are linear and non-linear, bilateral and unilateral, distributed and lumped, time invariant and variant. Okay. So coming to active elements, so voltage source and current source. What is a voltage source? Again, voltage source or independent voltage sources are of two types: ideal voltage source and a practical voltage source. Ideal voltage source is nothing but you'll have a voltage source and there won't be any source resistance or the internal resistance of the source. Okay, so this is nothing but you'll have the full voltage here, okay, at the open circuit terminals. This is nothing but your ideal voltage source. And what is a practical voltage source? You'll have a source resistance in series with the voltage source. Okay, in series with the voltage source, you'll be having a source resistance or the internal resistance of the source. Okay, and V out is different from Vs. There will be drop across this internal resistance. Okay, similarly, what is a ideal current source? Ideal current source will, or a practical current source. If I first talk about the practical current source, what is a practical current source? A current source in parallel with a resistance. Okay, a current source in parallel with a resistance is nothing but a practical current source. What you call this? Vs and Rs. Rs is the series resistance. Rp is the parallel resistance. Okay, Is in parallel with the resistance is nothing but a practical current source. And so if this is Is, this is I out. I out is different from Is. There will be some current flowing here. Okay, so this is a practical current source and this is a practical voltage source. So what is an ideal current source? When the resistance is infinity, that means no current flows here. Okay, so open circuit, as we have just seen, open circuit, there won't be any current flowing. So this is an ideal current source with an open circuit in the parallel resistance. Okay, this is nothing but Is is nothing but equal to I out. Is is nothing but I out. Okay, voltage source and current source. So there is one formula. You can convert a practical voltage source into a practical. What is a practical voltage source? A voltage source in series with a resistance. And what is a practical current source? A current source in parallel with the resistance. Okay, you can convert this voltage source into a current source, this voltage source into a current source, and vice versa. Okay. So, from this, what is Is? Is is equal to Vs by Rs. Okay, so R and Rp is equal to Rs. Rp is equal to Rs. So if I am having this one, I can get this. A practical voltage source can be converted to a practical current source by using this formula. Is is equal to Vs by Rs and Rp is equal to Rs. Similarly, a practical current source can be converted to voltage source like this. Vs is equal to Is into Rp and Rs is equal to Rp. Okay, Rs is equal to Rp. So practical current source can be converted to practical voltage source, as well as practical voltage source can be converted to a practical current source. So then we have what you call as dependent sources. What are the dependent sources? VCVS, VCCS, CCVS, and CCCS. What is VCVS? Anyone? What are these? So these are dependent sources. The previous one are, these are independent sources. These are dependent sources. So dependent sources are nothing but, see, VCVS is voltage controlled voltage source. Okay, voltage controlled voltage source, voltage controlled current source, current controlled voltage source, current controlled current source. Okay, you have four type of dependent sources: voltage controlled voltage source, voltage controlled current source, controlled voltage source, and current controlled current source. VCVS, if I draw the circuit, it will be and dependent sources are represented like this. some A into, it's a voltage controlled voltage or voltage dependent voltage source. This can be called CVS or VDVS, voltage dependent voltage source or voltage controlled voltage source. Okay, so A into Vx. So Vx can be voltage across any other. So this can be Vx. So this value, voltage source value, depends on some, this is a constant A into Vx. What is Vx? Vx is voltage across this resistor R. Okay, so this is nothing but your voltage dependent voltage source. Okay, and next similarly current dependent voltage source. So if I say this is Ix, this will be again A into Ix. Okay, and importantly, what are the units of this A into Ix? The units of A into Ix. See, remember this is CCVS. This is CCVS, current controlled voltage source. What is this? This is a voltage source, right? Voltage source will have units as volts. Okay, the units are volts. It may depend upon the value of current here, but the units are volts. Okay, current controlled voltage source, voltage controlled voltage source. Next, VCCS, voltage controlled current source. Again, this is an R, and this is voltage Vx. So this is again, I can call it as A into Vx. Okay, and CCCS, current controlled A into Ix. Let me have a resistor here so that there won't be confusion. Call this as R1 and R2. Okay, Ix is nothing but the current flowing in R1. Okay, and importantly, what is the units of this? A into Vx. A into Vx quickly. This is voltage controlled current source. So the current source will have amperes units. So again, this is a current source. It may depend upon the voltage here, but this is a value of current. Okay, A into Vx. Okay, these are what you call dependent sources. You have four type of dependent sources and two type of independent sources. Voltage source and current source are independent. You have again practical voltage source and ideal voltage source, practical current source and ideal current source. Similarly, you have four types of dependent sources: VCVS, CCVS, and CCCS. Okay. So, and this is again important. Internal resistance, ammeter internal resistance 0, voltmeter infinite. This is very important for instrumentation guys and all, because you even for electrical and EC also, sometimes you'll get this ammeter is given. What is the internal resistance of an ammeter? Ammeter internal resistance will be very low. If not given, you have to take it as 0. Voltmeter internal resistance, if given, you'll take it, otherwise infinity. Current source infinity, voltage source infinite, voltage source 0. This is important, right? Voltage source, what is the internal resistance? Ideal voltage source, internal resistance is infinity. Ideal voltage source, we just what you call went through this. Ideal voltage source, internal resistance is 0, or the source resistance is nothing but internal resistance, it is 0. Current source infinity. But whereas it when coming to voltmeter, voltmeter it is infinity, ammeter it is 0. Okay. The reason behind this is ammeter 0 in the sense ammeter is connected in series. Always remember, ammeter is connected in series in any circuit, and voltmeter is connected in parallel in any circuit. Okay, voltmeter is connected in parallel. Okay, if it is having any resistance, what happens? The current flows through this, and the reading it has to take, it will vary. So similarly, if an ammeter has any internal series resistance, what happens? there will be voltage drop across this, which causes a change in current flowing through it. So that is why the internal resistance is 0 for current source and infinity for voltage source. Sorry, voltmeter and ammeter. Okay, voltage source and current source is different, and voltmeter and ammeter is different. Okay. Next, generally independent sources supply power to the circuit, or they can be placed in any circuit in such a way that they absorb power from the circuit. This is very important. So we always think that independent sources only supply power to the circuit. Okay, they can be placed in any circuit so that it can absorb the power from the circuit rather than giving the power. Okay, so for example, okay, before that, let me connect. Let me show you this. If voltmeter is connected, sorry, voltage source is connected, and this is a resistance. Okay, so this is a simple circuit. So I'll call it as 10 volt source and a 2 ohm resistance. So what is the current flowing? The current flowing in this is I is equal to 10 by 2, 5 amperes, right? So if I add one more current source here, a source of 2 amperes here. What is the current flowing in the circuit? What is the current flowing in the circuit? Anyone? What is the current flowing in the circuit? If I had a 2 ampere current source here, what's the current flowing in the circuit? Am I audible to everyone? See, what happens is a current source forces this current through flow it. Okay, so this will be the current flowing in the circuit, 2 amps. Okay, this voltage source won't define any current, so voltage source won't be defining any current. And if you see, the current is flowing in this way, so this, instead of supplying energy to this circuit, it is absorbing energy. Okay, supplying energy to the circuit, it is absorbing energy. The independent sources supply power to the circuit. However, they can be placed in a circuit in such a way that they absorb power from the circuit. Okay. So next is network analysis and synthesis. What is network analysis and synthesis? So for any electrical network or circuit, you'll be given input. Okay, and you'll be given the network, and you have to find the output. This is nothing but you'll be given input, you'll be given the network or the circuit, and you have to find the output. Output is usually current through an element or voltage across an element. That is the output. So this is what you call it as network analysis. Okay, network analysis. And you are given input and output. Okay, you are given input and output, and you have to find the parameters of the network. You have to find the parameters of the network. That is nothing but your synthesis. Okay, giving network and the input, giving the network and the input, you have to find the output. This is nothing but analysis. Giving input and output, and you have to find the network parameters. This is nothing but synthesis. Okay, network analysis usually have only one answer, one solution, but synthesis will have multiple solutions. Okay, am I audible to everyone? Don't see any comments also. Okay. Okay, next coming branch, node, loop, and mesh. Branch, node, loop, and mesh. Okay, so node, a point A point where two or more active or passive elements are connected is nothing but a branch. Sorry, a node. Okay. So the node is where two or more elements, okay, passive or active elements are connected is nothing but resistance, capacitance, and inductance. This is nothing but a node. Okay, branch is formed between two nodes. Okay, two nodes. If I have two nodes, this is called as a branch. Loop, any closed path in the circuit can be called as loop. Any closed path in the circuit can be called as loop. Mesh, if the loop in the circuit does not enclose any other loops inside it, then that loop can be called as a mesh. For example, so okay, if two or more active or passive elements are connected, so these are all nodes. Okay, so okay, these three are one node. Okay, and these are all branches, and loop, any closed path is a loop. So how many loops and how many meshes in this? How many loops and how many meshes in this? Anyone? How many loops and how many meshes? Any answers? Got erased. See, you have two meshes and three loops. Okay, this is a closed path. If you see, if I call this as A, B, C, D, okay, E and F. Okay, A, B, C, D, E, and F is one more closed path. So any closed path in the circuit is called as a loop. But mesh is what? It should not have further closed paths. So this is one mesh and this is one mesh. So only two meshes and three loops. Okay, clear? Only two meshes and three loops. Is it clear, everyone? So difference between mesh and loop. Why am I not getting any responses? I don't know whether I'm not able to see or am I audible again? I want response from everyone. Am I going fast, slow? Are you able to catch me, or am I going very slow? Or see, these are basics, right? Basics of network analysis. I just want to refresh all those basics. I think most of you will be remembering all this. So what I want to do is I want to just refresh all these basics so that we can go see some good problems, which we can see, what you call, which we can do it very quickly, like simple MCQ type questions. Okay. So that is why I want to go again, like I want to just refresh all the basics of network analysis. Okay. Next, Kirchoff's first law or the current law. Kirchoff's laws. Next is Kirchoff's laws, KCL and KVL. So what is Kirchoff's current law? What is Kirchoff's current law? Kirchoff's current law states that the total current or charge entering a node or a junction is exactly equal to the charge leaving the node. Okay. So the total current entering or leaving the junction will be same. Okay, and it has no other place to go except to leave, as no charge is lost within the node. Okay, So this is nothing but Kirchoff's current law states that the conservation of charge. Conservation of charge. Okay, Kirchoff's current law states that all the currents entering is equal to all the currents leaving. See, if you see in this, there are I1, I2, I3 entering. I1 plus I2 plus I3 is equal to all the currents leaving. What are the currents leaving? I5 and I4. So I4 plus I5, or I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. Okay. Hence, the three currents entering the node I1, I2, I3 are all positive in value, and the two currents leaving the node I4 and I5 are negative in value. Then this means we can also rewrite this equation as I1 plus I2 plus I3 minus I4 minus I5 is equal to 0. Okay. At any node, the current entering is equal to current leaving. Okay. So this also means law of conservation of charge. Okay. Charge is conserved. Okay. Charge is not going anywhere, so it is conserved. Okay. I exiting is plus I entering is 0. Next, Kirchoff's voltage law. Kirchoff's voltage law or KVL states that in any closed path or any closed loop, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is equal to 0. Okay, all the voltage drops in any closed loop is 0. Okay. So in other words, algebraic sum of all voltages within the loop must be 0. The idea of Kirchhoff's law is law of conservation of energy. See here. So you have voltage drop between this resistance VAB, and VBC. Okay, if I'm going this clockwise direction, VAB plus VBC plus VCD plus VDA is equal to 0. All the voltage drops in the loop is 0. Okay. See, usually some people take clockwise directions, some people take anti-clockwise directions. Okay, it doesn't matter. You can take any directions, but try to follow one convention in all your what you call problem solving techniques, all your problem solving techniques. Whether your teacher follows one in one topic and other in the other topic, you better go for one direction so that it would be easy, or you won't be having any confusion. Okay, so VA plus VB plus VC plus VDA is 0. Starting at any point in the loop, continue in the same direction. Okay, continue in the same direction, noting the direction of all the voltage drops, either positive or negative, and return back to the same starting point. It is important to maintain the same direction, either clockwise or anti-clockwise, or the final voltage sum will not be equal to 0. We can use Kirchhoff's voltage law when analyzing series circuits. Okay, so this is important. Kirchhoff's voltage law mostly will use for series, and Kirchhoff's current law will use for parallel, because parallel current divides, right? You'll be having node and there will be current division. But in Kirchhoff's voltage law, the drop will be in a series circuit. That's why for analyzing series circuits, we'll use KVL. So people usually get doubt this, where should we use KCL and where should we use KVL? Actually, the main concept is wherever you get less number of equations to solve. That is the main concern. So for series circuits, it's better to use KVL. For parallel circuits, it's always better to use KCL. Okay. Am I clear so far? Any doubts? Any clarifications needed? Am I clear? So next is series connection of resistance and voltage division. Okay, series connection of resistance and voltage division. Okay, two or more elements are said to be in series when same current flows through them. So when do you call two elements in series, two or more elements in series? When same current flows through them. Okay. Remember this is same current, not equal current. Okay. So if I'm having two circuits, 4 amps is flowing here. 4 amps is flowing here. Can I call these two as series elements? No, right? This is equal current flowing, but not the same current, right? Or I can say in a parallel circuit also. If there is 4 amps here and 4 amps here, I cannot call these as in series because it's not the same current. Okay, the current is getting divided here and equal current is flowing. So these are not series elements, these are parallel elements. Okay, what is series? Series is nothing but the same current should flow through this. If I have another resistance here, so these two, the 4 amps will flow from through R1 and R2. So the same current is flowing through these. So then this is called as a series element. And this can be called as series elements. Okay. So series elements. And voltage division, right? So I'm having a voltage source V, resistances R1 and R2. Say the current flowing is I. Okay. So if I apply KVL in this, what will happen? This is minus V. Okay, the first thing you go, you have to consider that. So minus V plus I into R1 plus I into R2 is equal to 0, or V is equal to I into R1 plus R2. Okay, so the total resistance in series is nothing but R is equal to R1 plus R2. R is equal to R1 plus R2. Okay, so if I call this as V1 and this as V2, voltage across resistance R1 is V1, voltage across resistance R2 is V2. So what is V1? V1 is nothing but I into R1, or I can be written as from this. From this, I can be written as V by R1 plus R2 into R1. Similarly, V2 can be written as I into R2 or V by R1 plus R2 into R2. Okay, these two are important. Voltage division and current division, voltage division rule. So voltage division rule, voltage across any element in series is nothing but total voltage into same resistance by total resistance. Here also total voltage into same resistance by total resistance. Voltage division rule, you have to remember V1 is equal to V into R1 by R1 plus R2. Okay, if I have one more resistance, you can call it as R1 plus R2 plus R3. Okay, so same resistance by total resistance. Okay, voltage division rule in series elements. Next, current parallel connection and current division. Parallel connection. Two elements are said to be in parallel. This is important when both the ends of one element are connected to both the ends of other element. You have to remember this parallel connection when both elements are said to be in parallel. When both the ends of one element are connected to both the ends of other element, then you can call them as parallel. Parallel connection. You're having two resistances, say R1 and R2. So when can I call them in parallel? If both the ends of one resistor connected to both the ends of the other resistor, then I can call them in parallel. Okay, this is important. Both the ends of one resistor is connected to both the ends of other element or other resistance, then you can call them in parallel. Okay, and current division. So I'll take a current source I. This is I1, I2. Okay, if I apply KCL here, so parallel the voltage is same. Okay, voltage is same. In series the current is same. Okay, so I is equal to I1 plus I2 is equal to I1 is nothing but V by R1 plus V by R2, or I can also be written as V by R, total resistance. V can be or I can remove V from this. This is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Okay, in series you have seen R is equal to R1 plus R2. So generalized R1 plus R2 plus R3 plus so on. Here in parallel, 1 by R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3. And so on. Okay, parallel resistances in parallel are equivalent to the sum of all the resistance, reciprocals of resistance, or I can say conductances. G equivalent is equal to G1 plus G2 plus G3 plus so on. Okay. So this is parallel connection and current division. If I see what is I1, I1 is equal to V by R1. So V is nothing but I'll write it here. So R equivalent is, if I take the LCM, of this, it will be R1 R2 by R1 plus R2, right? So V is nothing but total I into R equivalent by R1. Total I into R equivalent by R1. I'll erase this. So I1 is equal to I into R equivalent R1. So I into R equivalent is R1 R2 by R1 plus R2. So R1 and R1 gets cancelled. This is I into R2 by R1 plus R2 I1. This is important. This is very important. So if you want to note it down, you can write it. So I2 again will be equal to I into R1 by R1 plus R2. Okay. So if you see this, what is the current flowing in one resistor? It is the total current multiplied by the opposite resistance divided by the total resistance. Similarly, I2 is equal to I into R1 divided by total resistance. Whereas in voltage division, what you see, total voltage into same resistance by total resistance. Current division, current into opposite resistance by total resistance. So voltage division rule and current division rule both are very important. Am I clear so far? Any clarifications needed? I think the annotations is getting deleted or erased every time. Next time I'll bring this in keynote presentation so that as Mr. Dinesh sir is saying, I can easily annotate them. I think this PDF annotation is a bit tough here. I'm unable to annotate it properly. Is it clear so far? Okay, two equal resistors R and R in parallel, then the equivalent resistance is quick. So what is the equivalent resistance if two resistances R and R in parallel? What is the equivalent resistance? Anyone? Two equal resistances R and R in parallel. What is the equivalent resistance? Half, right? Correct. So R equivalent is equal to R1 R2 by R1 plus R2 or R square by 2R. So this is R by 2. If three equivalent resistances are connected in parallel, what is the equivalent resistance? If three equal resistances, three equivalent resistances, sorry, yes, if three equivalent resistances are connected in parallel, then everyone, if three equal resistances are connected in parallel, R by 3, okay, n resistances, it is R by n, right? If n resistances are connected in parallel, it is R by n. Equivalent is R by n for n resistance. If say R and 2R are connected in parallel, what is the equivalent resistance? Okay, two resistors R and 2R are connected in parallel, then what is the equivalent resistance? Two resistors, say R and 2R are connected in parallel, 2R by 3, right? So 2R by 3, this is very important. So R and 2R are connected in parallel, then it is 2R by 3. So R equivalent is R into 2R by 3R. So this is 2 by 3R or 2R by 3. Okay, and this is important. So say for 3 and 6 are 6 ohms, 3 ohm and 6 ohms are connected in parallel, then it is 3 ohms and 6 ohms are connected in parallel. Answer is yes, 2. Right? Okay, yeah. Tell me if 6, 3 and 2 are in parallel. 3 resistors, 6, 3 and 2 are in parallel. So these are, you have to remember them quickly. 6, 3 and 2 are in parallel. What is the equivalent resistance? 6, 3 and 2 are in parallel. 1, right? Hmm. Three resistors, 6, 3 and 2. How will you solve this? 6 and 3 are in parallel. The equivalent is 2. 2 and 2 parallel, 1. You have to remember this. Whenever you see 6, 3 and 2, you should directly write it as 1. Okay, you should not keep on calculating again. 6, 3 and 2 is always 1. This will be helpful in many of the problems. Okay, 6, 3 and 2. Okay, R, 2R, R and 2R, 2R by 3. Okay, R2 and R and 2R. If 6 and 3 are in parallel, what happens? The bigger one by 3. Okay, 6 by 3 is 2. Okay, similarly 10 and 5, 10 by 2. sorry, 10 by 3. Okay, 10 and 5 in parallel is 10 by 3. The bigger one by 3. Remember, R and 2R, 2R by 3. Okay. Okay, 4 and 4 is 2 ohms. Okay, 6 and 6 is 3 ohms. 12 and 12 is 6 ohms. Two equal resistance. Okay, this is same. 6 and 3 is 2. 12 and 6 is 12 and 6. 12 by 3, 4. And similarly, one more. 12, 6 and 3. Fastly. 12, 6 and 3. See this 12 and 6 parallel. What is this? This is 12 by 3 is 4. 4 and 3 in parallel. 4 into 3 by 7. Okay, 12 by 7. Series and parallel connection of sources. This is important. Twelve by 7. Okay. Right. Next, series and parallel connection of sources. Many people usually get confused in this. Okay. So first, I'll check with the voltage sources. So this is V1 and V2. Okay, what is the equivalent? The equivalent is, see if I this way, okay, this I can call it as V equivalent. Happens. So this is plus V. V is equal to or V minus V1. V minus V1 minus V2 is equal to 0, or V is equal to V1 plus V2. This is what you call as voltage sources in series. Series aiding. Okay. There is something called as series opposing. Okay. This is V1 and V2. Voltage is either V1 minus V2 or V2 minus V1. If I call this as plus and minus, then this can be said as V1 minus V2. Okay. So the same as voltage. If the directions are same as V1, so this will be V1 minus V2. Okay. So this is series in series opposing. Series aiding and series opposing. Okay. Similarly, current sources. This is I1, I2. This I equivalent is I1 plus I2. Parallel aiding. Parallel aiding. I is equal to I1 minus I2. Parallel opposing. Okay, series aiding, parallel aiding, series opposing, and parallel opposing. Okay, and okay, so far clear. Now the important is current source in series with a voltage source. So anyone? Current source in series with a voltage source. What is this? Current source in series with a voltage source. What is the equivalent? Anyone? Current source in series with a voltage source. Okay, current source in series with a voltage source will be something like this. V and I, which is equivalent to current source I. Okay, what does this mean is this current source, whatever be the value of this voltage source, it will only force the current. Okay, say this is 10 amps. This will force the 10 amps to flow through this circuit. Okay, irrespective of the value of voltage source. Okay, so it doesn't matter whether your voltage source is of 1 volt or 100 volt. It doesn't matter, because if I have a resistor here, what is the current flowing through the resistor? It's always 10 amps irrespective of the voltage value. Okay, irrespective of the voltage source value, the current is always 10 amperes. So a voltage source in parallel, sorry, in series with a current source is equivalent to a current source. Okay, is this clear? Is this clear? Because many people have doubts in this. That is what. Okay, similarly, a voltage source in parallel with a current source. Now, can you tell me what is this? Voltage source in parallel with a current source. Can you tell me what is this? Voltage source in parallel with a current source. Yeah, please allow me, Rahul, so I can see the comments in my mobile actually. I'm able to see the comments here, so that's what I and okay, voltage source in parallel with the current source is always a voltage source. Why? Because is whatever be the value of the current source here, the current whichever flows in the resistance is equal to V by R. Okay, the current that flows is V by R. Okay, it doesn't depend upon this current source. That is why voltage source in parallel with current source is always a voltage source. Current source in series with the voltage source is always a current source. Is this clear, everyone? Because this is important. Okay. Okay. Voltage source in series, and there is one more combination. One more combination which cannot exist. V1 and V2. Okay, this cannot exist. Okay, you cannot. If electrical people are there, this is called as synchronizing. You can't connect different voltage sources in parallel. Two different voltage sources cannot be connected in parallel. Similarly, two. Okay, synchronizing in case of what you call transformers or alternators. Okay, so two voltage sources of two different voltage sources cannot be connected in parallel. there'll be circulating currents, there'll be some other nuisance in this. So you cannot connect two voltage sources in parallel, two different voltage sources in parallel. Only possibility is if V is equal to V1 is equal to V2. Okay. Similarly, I is equal to I1 is equal to I2 can only happen. If this is not equal, it cannot exist. Okay. Clear? Yeah. Quickly, this small problem. Answers anyone? 12 ohms, 12 ohms, 12 ohms. There's three resistors connected in such a pattern. So any answer here? Any answer here? Any answers? 12 ohms, 12 ohms, 12 ohms. Hey, this showing that so. Okay. Okay, 4 ohms. Okay. Okay. So tell me, how are these three resistances connected? So did you find anything here? Connection, series, parallel, or no series, no parallel, star, delta? Yes, all are in parallel, right? So remember the definition of parallel resistances. How do you define two resistances or two elements in parallel? Again, the definition, back to the definition, as I told you, when do you call two resistances in parallel? When do you call two resistances in parallel? Two elements are said to be in parallel when both the ends of one element are connected to both the ends of other element, right? When both the elements of one element, sorry, both the ends of one element is connected to both the ends of other element, then only you can call them as in parallel. So if you see this, let me call this as A1, B1, A2, and B2, A3, B3. B3. So these two resistances are in parallel. These two resistances are in parallel. Now coming to these two, what is this? B2 and A3 are connected, A2 and V3 are connected. So all the resistances are connected, and both the ends of all the resistance are connected to each other. So this is something like this: 12 ohms, 12 ohms, and 12 ohms. So three equal resistors in parallel. The equivalent is 4 ohms. 12 by 3 is 4 ohms. Right? Clear? 12 by 3 is 4 ohms. By 3 is 4 ohms. Okay? No, this one. This is a gate question, but you can directly solve this. Everyone try to do this. Everyone try to do this. I'll give you 2 minutes. I brought this question because this can be directly answered. That is why I brought this. I don't want in this. See, HAL is basically MCQ type questions. So this can be an MCQ because this you can directly say the answer from this, or with minimum calculations you can do the answer. So everyone try this. Try this and tell me. See, any series parallel combinations you can see. You can unmute and talk. Only we are three people, so you can unmute and talk. Any series parallel combinations you can see in this? Right, 3.8 ohms. See, these two are in. Again, these two are in series. This is 2 ohms here. Okay, if you see this, 6 ohms and 3 ohms. How are these two? 6 ohms and 3 ohms. 6 ohms and 3 ohms. 6 ohms are in parallel, right? These two, 6 and 3 are in parallel. Okay. So what is the equivalent when 6 and 3 ohms are in parallel? What is the equivalent resistance when 6 and 3 ohms are in parallel? Quickly. You can see both the ends of this 6 ohm resistor connected to both the ends of this 3 ohm resistor. So 6 and 3 in parallel, R and 2R in parallel, it's 2R by 3, right? R and 2R in parallel, it's 2R by 3. So 6 by 3 is 2 ohms. So if you see these 6 and 3, these 6 and 3 are also in parallel. Or you can say 6, 3 and 2 are in parallel. It's like if I redraw it, it is 1 ohm here, 0.8 ohms here. And this is 6 and 3 parallel is 2 ohms. Again 2 ohms. And here it is 2, 6, sorry, 3, 6 and 2. Okay, 6, 3 and 2 is 6, 3 and 2. We already discussed it's 1 ohm, right? It's 6, 3 and 2 is 1 ohm. 6 parallel with 3 is 2, 2 parallel 2 is 1. So it will be 1 ohm to 0.8, and this is 2 plus 1, 3. Okay, 3 parallel with 2. 3 parallel with 2 is 6 by 5. Okay, 6 by 5 is 3 parallel with 2. 3 into 2, 6 by 3 plus 2, 5. 6 by 5 is 1.2. So this is 1, 1.2 and 0.8. So total is 4 ohms. Somebody got us 3.8. No, it's not 3.8. It's 4 ohms. Okay. The answer is 4 ohms. Clear, everyone? Understood? You always have to find out the series and parallel combinations. Directly saying, you can say that these two are in series and these two are in parallel. These two are in parallel. So what happens? 6, 3 and 2 parallel is 1. 6 and 3 parallel is 2. 6, 3 and 2 is 1. 1 in series with 2 is 3. 3 and 2 parallel becomes 1.2. Series with 0.8 and 1 becomes 4 ohms. 3 ohms how? 3 ohms is like this is 2 in series is with 6, 3 and 2. 6, 3 and 2 is 1. 1 and 2 in series will become 3 ohms. Okay, if you want, I can have one more step here. This is 2 ohms and this is 1 ohm. We'll get something like this. This is 2 ohms. 2 plus 1 is 3 ohms. 3 and 2 will be in parallel. Clear? Shall I repeat or is it clear? Final answer is 4 ohms. Final answer is 4 ohms. 1 plus 1.2 plus 0.8. You have a 0.8 here. 0.8. Yes. 1 plus 1.2 plus 0.8. Oh, it's 3 ohms. Sorry. Plus 1.2 plus 0.8 is 3. Sorry. It's not 3. Sorry. I'm sorry. It's 3. It's not 4. 3. 1 plus 1.2 plus 0.8 is 3 ohms. Okay with everyone? Okay. Next is one more important technique. It's called source transformation technique. Source transformation technique. We have seen that source transformation technique, I think I have covered. Voltage source can be transformed to a current source, and current source only the practical voltage sources and practical current sources can be converted. Practical voltage source is nothing but Vs in series with Rs. Practical current source is nothing but Is in parallel with Rp. Okay, so here it is 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 equal to Vs by Rs. Rp is equal to Rs. Here it is Vs is equal to Is into Rp. Rs is equal to Rp. Okay, source transformation technique. And then delta to star and star to delta. Delta to star and star to delta. So there are small derivations for this. I don't think those are important. Only thing is you have to remember this delta to star and star to delta techniques, the equivalent resistances. So I'm having a delta resistance, delta circuit, and this is a star. Okay, this is how it looks. It looks like a delta or a triangle. Okay, delta to Y or star. Okay, so what happens? This is my equivalent resistances RA, RB, and C. So N1, N2, N3. So N1 this is R1, N2 this is R2, this is R3, N3 this is R3. Okay, so from this R1 is equal to RB into RC. Okay, you always have to remember delta to start. Denominator is same. What is denominator? Denominator is RA plus RB plus RC. Sum of all the three resistances, RA plus RB plus RC. So I'm converting this delta into star. So what if I want R1? What I have to do? The denominator part is RA plus RB plus RC. And if I want R1, what I have to do? To multiply these two resistances connected this node. Okay, N1 is connected to RB and RC. So this is RB into RC. Okay, so R1 is nothing but RB into RC by total resistance. If I want R3 again denominator is same, RA plus RB plus RC. What will be the numerator? RA into RB. Numerator is nothing but for R3 it's RA into RB. So similarly for R2 is again denominator is RA plus RB plus RC. Numerator will be RA into RC into RA into RC, RA into RB for R2 and R3. Okay, delta to start, it starts with D, so denominator is same. In this is the simplest way you can remember. Delta to start, denominator is same, which is equal to RA plus RB plus RC, and the numerator will be multiplication of the resistances connected to the same node. Okay, on the same node. Okay, again, star to delta to star, it's the denominator same. Star to delta, it's the numerator the same. Numerator is nothing but LCM of all this. See, once the numerator will be plus R3 R1 divided by, see, the resistance is these two nodes except those and 3 R1. So this is R1. RA is the numerator is same R2, R2, R3, R3, R1 divided by the non-touching resistance. Non see, the numerator is R1, R2, R2, R3, R3, R1. Okay, a simpler way to remember. Delta to star, denominator is same. Star to delta, numerator is the same. Okay, clear? Clear? Tell me, if three equal resistances are connected in delta, if three equal resistances are connected in delta, what is the equivalent resistance in star? Okay, RA is equal to RB is equal to RC is equal to R. What is R1? What is R2? What is R3? Is equal to R. C is equal to R. What is R1, R2, R3? So I want to convert from delta to star. Remember delta to star. Try to do this. Important. This is important. Try to do this. RA is equal to RB equal to RC is equal to R. What is R1, R2, R3? Anyone? from my side is it, sir? Acha, is it? Surjit, you need to see. Yes, it's R by 3. It's R by 3, right? Okay. Always remember, if all the three are equal, I can call it as R delta is equal to 3 times R star, or R star is equal to R delta by 3. Okay. R delta is equal to 3 times R star, or R star is equal to R delta by 3. Sir, I think there is some connectivity problem, lag, breaking voice sometimes. Oh, okay. My internet is very stable actually. Is it from my side or is it from your side? I know the annotation is becoming some problem sometimes. Not sure about the voice. Am I clear now? Am I audible properly now? Breaking was sometimes. Surjit, are you able to see the screen? Yes, no, I can show. Okay, see the slide. Okay. Okay, is my voice audible now? You understood this, right? R delta equal to 3 times R star, and R star is equal to R delta by 3. Okay. Okay. There is one more concept called as Wheatstone bridge. Wheatstone bridge. So Wheatstone bridge is something like this. So why is Wheatstone bridge used? Wheatstone bridge is used to measure unknown electrical resistance by balancing the two legs of the bridge circuit. One leg which is having an unknown component. Okay. So I want to find Rx here. For example, I want to find Rx here. What I'll do is R1 and R3 are known resistances, but these two are fixed resistances. And I'll be having an R2 known resistance, which is a variable resistance. I'll vary this resistance R2 such a way that the bridge gets balanced. That means the voltage in this voltmeter or the galvanometer shows 0. That means the potential here D and B will be same. Okay, VD is equal to VB. No current flows between D and B. Okay, no current flows between D and B. So then what happens? This galvanometer doesn't show any reading. This condition is called as bridge balance condition. What is called? This is called as bridge balance condition. At bridge balance, what happens? R1 by R2 is equal to R3 by Rx. R1 by R2 is equal to R3 by Rx, or R2 by R1 is equal to Rx by R3. So by this I can find the unknown resistance value Rx. Okay, so balance bridge condition is very important. R1 by R2 is equal to R3 by Rx, or R2 by R1 is equal to Rx by R3. It's a balance bridge condition. So whenever you see a Wheatstone bridge, this is very important. Whenever you see a Wheatstone bridge, the first thing you have to check is for balance bridge condition. For balance bridge condition. So what happens under balance bridge condition? As I told you, there won't be any current flowing through this central limb. Okay, there won't be any current flowing through this central limb. So for example, yeah, this is what a Wheatstone bridge is. What is a Wheatstone bridge? For example, see, there are other bridges also. You'll see in measurements, that is not of much importance here. Or for example, under balance bridge condition. So this is R1, R2, R3, R4. So what is balance bridge condition here? Say this is R. Balance bridge condition is R1 by R2 is equal to R3 by R4, or which is equal to R1 R4 is equal to R2 R3. Okay, you can check this or this. So if this is happened, what happens? The current through this resistance will be zero. Okay, or the voltage across this resistance will be zero. Okay, so can someone tell me what is voltage zero condition? Is it short circuit or an open circuit? Voltage zero. Voltage zero condition, is it a short circuit or an open circuit? Is it a short circuit or an open circuit? Voltage zero condition. Anyone? Short circuit, right? Voltage zero condition is short circuit. What is current zero condition? What is current zero condition? It's an open circuit, right? See here what is happening, no voltage is there, no current is there. So depending upon the circuit, this is very important. Depending upon the circuit, you can consider it as a short or an open. Okay, you will get a similar answer in both the cases. Okay, trust me, you will get the similar answer in both the cases. We'll if you want we'll see with examples also. Okay, you'll get a similar answer if both what you call if I consider equal what you call short circuit or an open circuit. Okay, for example, if you see this, the same bridge, find the equivalent resistance between A and B terminals. All resistances are equal to R. All resistances are equal to R. How will you do this? How will you do this? Star, delta, delta, star, any other technique? What is the equivalent resistance between A and B terminals? Any answers? You can convert the, see here you'll have three resistances, all are equal. You can convert delta to star, star to delta, any other technique you want to follow, you can do that. It's R, right? Okay, how did you do it? How did you do it? Surjit, how did you do it? See, remember, first thing when you see a Wheatstone bridge, you have to check for lower delta to star. Okay. See, first thing, whenever you see a, everyone look at the screen. Whenever you see a Wheatstone bridge, first thing you have to check is the balance bridge condition. The first thing you have to check is the balance bridge condition. Is the bridge balanced here? Delta to star, one time gives R by 4 and adding 4R by 3 parallel with 4R by 3. Okay. Okay. See here, this is a Wheatstone bridge, right? Clear? Is it clear? Is this a Wheatstone bridge? So whenever you see a Wheatstone bridge, the first thing you have to do is you have to check for balance bridge condition. Whenever you see a Wheatstone bridge, you have to check is the balance bridge condition. So is the bridge balanced? Can you see it? So this R by R is equal to R by R. It's balanced, right? Is the Wheatstone bridge balanced? Are you able to see it's a Wheatstone bridge, right? It's a Wheatstone bridge. right? Yeah, it's a Wheatstone bridge and it is a balanced Wheatstone bridge. So when a Wheatstone bridge is balanced, what happens is the central limb, as I told you, the central limb can be opened or shorted. Okay, it depends upon the circuit. Okay, it depends upon the circuit. Many people take it as an open circuit. Even if you consider it as a short circuit, you'll get the same answer. First, let me open this. So because no current flows through this resistance does nothing in the circuit. Okay, you can literally open this. Okay, because this is an open circuit, no current flows through this. Because these two are at the same potential, no current flows between the equal same potentials, right? Okay, so no current flows through this. What happens? This will become something like this. R, R, R and R. No current flows through this. Okay, so this is how it happens. So now what happens? How are these two resistances and these two resistances? Anyone? What are these two resistances and these two resistances? How are these two resistances? Series, right? So R and R in series. What is the resistance? Equivalent resistance? It's 2R. Again, it's 2R here and 2R here. What is now 2R parallel with 2R? 2R parallel with 2R is 2R parallel with 2R is R. Clear, everyone? Am I clear? Clear, right? So if balanced Wheatstone bridge, whenever you see a balanced Wheatstone bridge of all resistances equal, the total resistance is equal to R. Clear? See, again, there is one more method. See, when I say this can be taken as open circuit or short circuit, now I'll consider it as a short circuit. What happens? So no voltage between these 2 points. So zero voltage is a short circuit point. So these are something like this. So these two are in parallel. R and R parallel is R by 2. These two are in parallel again, R by 2. R by 2 in series with R by 2 is R. 2R by 2 in series, yes. Clear? This is how you can consider a Wheatstone bridge. So whenever you see in any circuit, whenever you see a balanced Wheatstone bridge, what you can say that if all the resistances are equal, then you can call it as then the total resistance is equal to R. Okay, so whenever you see a Wheatstone bridge, the first thing you have to check is balance bridge condition. Okay, you have to check his balance bridge condition. So without checking the balance bridge condition, never convert delta to star or star to delta or nothing. Okay, if the bridge is not balanced, then you have to do all those delta to star conversion and all. Okay, okay, if the bridge is not balanced, then you have to do all those star to delta and delta to star conversions. So many people only take this as open circuit, only some people take this as short circuit, but you can take any of them. And see, in large circuits, what happens is it's better to consider them as open circuit than as a short circuit. Okay, so that way you can see, for example, if this is 2R and this is 2R. So now tell me, which is better to take it as a short circuit or as an open circuit? It's better to take it as an open circuit, right? See, that is one thing you have to always think of it. Okay, it depends upon the circuit to circuit. You'll get the same answer, whichever method you do it. Okay. So this is about Wheatstone bridge. So these are some of the basics of network theory. We'll see some important problems and other circuit theorems, problems, small problems, because I don't want to go into much of calculations because you won't be allowed calculators and all. So I don't want to go into much of larger problems. That's why I've given a Wheatstone bridge, in which also you don't have to convert a delta to star. Even if you have to convert a delta to star, they'll be giving like equal resistances or something like that, so that it's easier to calculate. The main objective is to test the concepts, not the problem solving ability or the calculations. Okay, so this is for today. We'll see in the next class the other concepts and some important bits, multiple choice questions, and we'll go for some theorems in the next class. Okay. Okay, I hope this is clear. You must be clear in parallel, series parallel. One of this is an important question. Okay, series parallel combinations. You have to remember this is important. Okay. Okay, there are some important questions, and we'll see in the next class. Okay. Okay. Thank you. Clear? Any doubts in today's class? Any doubts? Any clarifications needed? Shall I repeat any of these concepts? I think these are pretty basic concepts. I think, yeah, thank you.